Good day, everybody. How are you all doing? Hope you are doing great today. Okay, so like you know, I start my lecture, my videos with a joke on statistician. So this joke is interesting. Why did the statistician bring a bat to a casino? Because he wanted to hit a home run on the odds. Okay. So kidding aside, let's continue with what we discussed last time, which is a uniform probability distribution. And then I told you I'm going to show you an application of uniform probability distribution. Okay, so let's get started. So let me share my screen with you. Okay, so like we discussed last time, probability on the vertical axis and some random variable value on the horizontal axis. Okay, so this is random variable, any random variable. Last time we discussed about how long you have to stop at a traffic signal when it turns red. That was the random variable, time. Okay, and we have probability on the vertical axis. Okay, and we were talking about uniform probability distribution. That means within an interval, the probability will remain constant, hence the name uniform. This is your uniform probability distribution. Uniform probability distribution. Notice it is not bell-shaped. Okay. And it's uniform, as I mentioned, the probability within the interval that's starts from A to B on the horizontal axis. Probability value at each point between A and a B is constant. This is constant. This is last time we indicated by H. Okay, and this is constant. Okay, this is H on this side, H over at A value also, and it is constant. So it's a uniform probability distribution. Now today I told you I'm going to show you an application of uniform probability distribution. How will I do that? Okay, so let's get to the center of this distribution, which is the mean, somewhere over here. Okay, my drawing is not all that hot, so let me start again. Try to make it vertical as possible. Okay, so okay, that's your mean. Okay, and we are going to go K standard deviation. K is just any number. It can be 1, it can be 2. Actually, it cannot be 1. I'll explain it to you later. K is just a number. So let me draw another vertical line. Okay. Remember, we have gone K standard deviation from the mean on the center. On the right and on the left also we'll go an equal distance of K and draw another vertical line. Let me see if I can make it more straight, vertical. So, somewhere like this, yeah. Okay, this is also K. So, we went K, any number greater than 1, any number greater than 1 times standard deviation, K times standard deviation above the mean, on the right, because the numbers increase from the mean on the right, and below the mean, let me put it here, and below the mean on the left. Below the mean on the left. Okay. So now we will discuss Chevyshev's theorem. Chevyshev's theorem states that at least 1 minus 1 over k square percent of the data will fall within k standard deviation of the mean. So let's apply it for k is equal to 2. Okay. So let's do two things. Let me move this up and let me change the color of the ink. And so we will use apply Chevyshev's theorem for k is equal to 2. Assume mu is equal to 20 and, oops, sorry. So I have to erase that. Mu is equal to 20 and sigma equal to 5. Okay, so let's first calculate 2 times sigma. So remember k is 2, 2 times sigma, this is k times sigma. K times sigma is 2 times sigma is 2 times 5 is equal to 10. So let's do mu plus k sigma, which is mu plus 2 sigma, which is 20 plus 10 is equal to 30, is equal to, pardon me, is 30. And mu minus k sigma is equal to mu minus 2 sigma is 20 minus 10 is 10. So what is Chebyshev then says? Okay, so let's change the ink further to make this little more interesting. Okay, so bear with me for a minute. Do not quit. I will explain to you what all Chebyshev's theorem mean. And I started with mu equal to 20, sigma equal to 5, k is equal to 2. So I went 2 standard deviation on the right of the mean, 20 plus 10 is 30. 2 standard deviation on the left of the mean, which is 20 minus 10 is 10. So let me draw this picture clearly for you. So again, let's draw a uniform distribution. So we're just going to draw the uniform probability distribution. Oops. So I'll have to erase this and make it vertical as possible. Oops, sorry. This is the best I can do. So let's, okay. So this is the center. Remember, the center is 20. And I went 2 standard deviation on the right of the mean to 30 over here, and 2 standard deviation on the left of the mean, which is 10 over here. So this is a uniform probability distribution. Mean is 20, sigma is 5, and k is 2. So let's draw 2 vertical lines at 10 and 30. Okay. So what is Chebyshev saying is 1 minus 1 over k. Remember, k is 2 square. So Chebyshev states, in this case, Chebyshev's theorem applied in this case will, so between 10 and 30, 1 minus 1 over 2 square, because yk is 2, so or 1 minus 1/4, or 4 over 4 minus 1/4, which is 3/4. So between 10 and 30, at least 3/4 or 75% of the data will fall. That's the beauty of Chebyshev's theorem. Basically, if you know that it is not a bell-shaped distribution, then you apply Chebyshev. You know the mean, from the mean subtract 2 standard deviation to the mean, add standard deviation. In this case, mean was 20, standard deviation was 5, and k is 2. So you get two limits. On the left is 10, on the right is 30. Draw two vertical lines. Because this is a uniform probability distribution, what Chebyshev's theorem states that at least 3/4 or 75% of the data in this case will fall between 10 and 30. Okay, so at least will fall, sorry, will fall between 10 and 30. Hence, it is called 1 minus 1 over k square law, where k is how many standard deviation away from the mean. Remember, the minimum value of k has to be greater than 2. I mean, greater than 1. In this case, we used k is equal to 2. So again, Chebyshev's the advantage of Chebyshev's theorem, it applies to any kind of distribution. It does not have to be normal. Like in this case, in our example, we applied it for uniform probability. It's not a bell-shaped. Uniform probability means constant probability within an interval, like I draw on this diagram. So then I applied Chebyshev, or 1 minus 1 over k square. K is 2. I found out that two boundaries within which 75% of the data will fall, which in this case is between 10 and 30. Okay, I stop here. If you like my video, give me a thumbs up. I would also like to know, where are you coming from? Where are you watching my video from? Please let me know that in the comment section. I really appreciate that. And if you like this video, share with your friends. You and your friends, please subscribe to my channel by hitting the red subscribe button. And please don't forget to watch me tomorrow when I'll be back with another interesting case. Okay, thanks for watching. Take care. Have a nice day.